Welcome to ChemDoodle Shorts. I'm Mary, your ChemDoodle Pro. Let's learn about cyclohexane chair conformations. Cyclohexane is a saturated cyclic ring composed of 6 carbon atoms and 12 hydrogen atoms. We often see it drawn as a hexagon. However, we know that molecules are not simply flat and static. They are always moving. Rings will adopt non-planar conformations to minimize ring strain caused by angular and/or torsional strain. Cyclohexane is no different. Cyclohexane is very stable because it has no ring strain. Its stability comes from the spatial arrangement of atoms in this chair conformation. In this conformation, a tetrahedral geometry exists about each sp3 hybridized carbon atom, allowing for nearly exactly 109.5 degree bond angles. Adjacent hydrogen atoms are also staggered. We see that this hydrogen on the carbon in the back is pointing up, while its neighboring hydrogen on the carbon in the front is oriented to the side, not vertically. As such, these spatial arrangements give the chair conformation the lowest potential energy of the cyclohexane conformations. Note the positions of the carbons in the chair conformation. They are positioned in an alternating manner: down, up, down, up, down, up. Notice the hydrogen atoms in yellow, 3 pointing up and 3 pointing down. These hydrogen atoms are in an axial position, as if they are up and down along the y-axis. They are parallel to one another and alternate pointing up and down too. The hydrogen atoms in green are equatorial. They are oriented outward around the middle of the molecule, like an equator. The equatorial hydrogens are angled slightly upward or downward, parallel to the ring's carbon-carbon bond, one step away. So this equatorial bond is parallel to this bond in the ring, or going in the other direction, this bond. This equatorial bond is parallel to these bonds in the ring. Keep in mind that each carbon in cyclohexane has 2 hydrogens bonded to it, one oriented upward and one projected downward. Also, each carbon has an axial hydrogen and an equatorial hydrogen. While cyclohexane has other conformations, it is most stable in the chair conformation. But it actually has 2 chair conformations. To convert to the other chair conformation, cyclohexane undergoes a chair flip. That doesn't mean that we simply flip the chair over. Cyclohexane undergoes a ring flip through rotations about the single bonds, so no bonds are broken. In the chair conformation on top, notice the red leftmost carbon is pointing down, and the blue rightmost carbon is pointing up. The positions of these carbons are reversed in the bottom chair conformation. Here, the red carbon is up and the blue carbon is down. Also, notice the position of the hydrogen atoms. In the chair conformation on the top, the yellow hydrogens are axial. In a chair flip, these axial hydrogens convert to equatorial hydrogens, as seen in the bottom chair conformation. Meanwhile, the equatorial hydrogens, in green on the top, become axial, pointing straight up or down in the bottom chair conformation. Take note that both of these chair conformations are energetically stable and free of ring strain. They both have tetrahedral geometries, bond angles of 109.5 degrees, and staggered hydrogen interactions. While they seem very similar, knowing these 2 different chair conformations becomes important when there are substituents on the cyclohexane. Thanks for watching ChemDoodle Shorts.